Okay, thanks for everyone for coming here. And so today I'm going to talk about some sort of soft skills in terms of modeling choices. Okay. So one of the most powerful aspects of structural approaches, I guess you guys have already learned from this previous lectures, is that it can give you information for policy designs. And a lot of research in empirical structural literature has been devoted to studying policy questions in an individual decision framework. Okay. And more recent development pushes toward equilibrium frameworks. But the question is, how do you make this choice? There is no absolute right answer because the modeling choice depends on the question you are trying to answer. Okay. So this talk, I will try to use a few examples to illustrate how you can make modeling choices in terms of individual decision versus equilibrium. Okay. So this is not going to teach you everything. It's just give you some illustration. Okay. This is a soft skill that you have to accumulate over time, but hopefully this lecture will give you some sense out of it. Okay. Okay, so the example I'm going to talk about is college major choices. It's a hot topic. It's being written by a lot of researchers. And the motivation of this kind of papers always starts from the observation that earnings differ substantially among college graduates with different majors. For example, engineers earn way more than education majors. And so one set of the question is why do students choose different majors? And how much of these choices explained by ability? And in particular, because we're talking about major choices, it's not a vertical kind of differences, it's more like horizontal. So in terms of major choice, you need to have multidimensional or major specific abilities, okay? So how much is due to ability, how much is due to preferences, and how much is due to information friction? Students just don't have a good sense of what they're good at. And to answer this question, is an individual decision model enough? Yes or no? Okay, so let's have a vote. Yes, hands up. No, hands up. The answer is yes. Because I'm asking why students make different choices. It's why the student make this choice, okay? So let me give you one example, individual decision model. One of the most well-cited papers in terms of individual decision model in major choices is perhaps this paper by Santiago 2004. So the goal of his paper is to estimate the monetary returns to particular majors. Of course, you have to take into consideration selection bias, okay? And the second is to find the underlying forces that explain student choices of majors. Okay, so in order to achieve those two goals, he estimated a dynamic model of college and major choice with 3 periods. First, individuals choose both a college and a major, or you just enter the labor market. So we start from high school graduation, okay? And if you enter the labor market, you are the absorbing state, okay? And then if you choose to enroll in a college, you receive new information about what you're good at, okay? So in specifically GPAs, has noisy information about your major specific abilities. And the individuals, they have some prior about their multidimensional abilities across different majors, and they receive GPAs and use those GPAs to update their beliefs about what they're good at, okay? So it's Bayesian learning, very standard. And then with updated beliefs, they can update their decision. They can change their major and or college and or just drop out and go to the labor market. Okay. So, and the third period, individuals work and receive earnings based on their past education choices. End of the model. Okay. So this model does have peers, okay, in terms of, in the sense that peer quality, specifically the average SAT scores of peers, matters for your own achievement and your utility in college. Okay, so both monetary payoffs and non-monetary preference payoffs, the peer quality would matter for both. Okay. So then after estimating this model, he did some simulation exercises to assess the importance of the following factors. First, quality difference across colleges. Second, major specific returns to your own verbal and math skills. And the third one is student preferences for different majors. Okay. So let's remind ourselves what's the goal of this paper. The goal of this paper is to explain individual choices. So in simulations, the author keeps the peer quality distribution unchanged. Okay, so there is no equilibrium effect. That's totally fine because your goal is to understand each individual student choices given all the other student choice. Okay, so I can keep the peer composition fixed. I can focus only on this particular student. Okay. So the findings from this model is that even after controlling for selection, there is large earnings premiums for certain majors. Engineering major just give you a high return. Okay. However, differences in monetary returns explain very little about the ability sorting across majors. And virtually all ability sorting you observe in the data is because of preferences for particular majors. Okay, that's the end of the paper. Questions? Okay. You guys are very quiet. If you don't ask questions, I can finish very early. That's not a good incentive, though. Go ahead. Oh, because you can shut down ability. You ask after estimating the model, you can shut down preference heterogeneity, you can shut down ability differences, and then see how much each component can explain. Sorry, the preference is, so the ability, there is observed ability type, and the ability type can be correlated with preferences, the standard discrete types. Okay. Okay, so now let's think about another example. Okay, students in countries like the US are admitted to colleges without claiming their major. They can go into a college and then spend a couple of years before they claim a major. Okay, so let's call this system S for sequential. So sequential choice of college first and then major is a sequential choice. Okay. However, most countries like China, college admissions are college major specific. A student has to choose a college major pair when you make your college enrollment decisions or application decisions, okay? So let's call this system J. J for joint choice of college and major. Okay, so the question number one is, what would happen to a student in system J, like the Chinese system, if she is allowed to choose her major after spending a couple of years in college? This is a question, okay? What would happen to a student if she's allowed to choose major after a couple of years in college, okay? Now, to answer this question, can we use a non-structural approach? Yes or no? Yes, hands up. No, hands up. No, because we're asking a counterfactual question. Okay, you need the structural approach in order to understand how students would make different choices under a different situation. Okay. Okay. Second question. Is an individual decision model enough? Yes, hands up. No, hands up. Yes. Because I'm asking, suppose I just say, for this particular student, I allow you to do certain things, what would happen? If that's my goal, then individual decision model isn't enough. I can keep all the other student choices as fixed. Okay? Now, a different question. Suppose my question is, what would happen if system J, the Chinese system, is replaced by system S, the US system? Okay, so how would welfare and educational outcomes change if all students can postpone their choice of major until after they learn about their fits to various majors? Now, that's my question. And to answer this question, is an individual decision model enough? Yes, hands up. No, hands up. Now we're talking. Unlikely. Because you need an equilibrium model because, for example, labor market returns to major could change if the supply of graduates from different majors change. That's a general equilibrium effect. Okay, so let's shut down the general equilibrium effect. Suppose we're only focusing on one cohort and the market is large, one cohort is tiny. Okay, so even if you don't want to consider general equilibrium effect, there is another layer of complication that you need to consider. That's a peer effect. Now I'm talking about allowing all students to make this major after college choice. And then the sorting of students will change. If the sorting of students will change, then peer quality will change. So there is no way you can fix peer quality anymore. Okay. So an example of equilibrium models is the following. So to the extent that college education aims at providing the society with specialized personnel, the joint system may be efficient if there is little uncertainty about what you're good at, okay? Because it allows for more specific training if the goal of college education is to give specialized labor force, right? And also it maximizes the interaction among students with similar comparative advantage, period. However, if non-trivial uncertainty exists, if you don't know what you're good at, then this joint system can lead to serious mismatch problems. So given the same population of students, efficiency comparison between these two systems depends critically on the degree of uncertainty faced by students, the relative importance of peer effect, and student sorting behavior that determines peer quality in equilibrium. Okay. Those are the three factors you need to consider in a model that that's aimed at answering the question I posed at the beginning. And we need an equilibrium model because the new admission policy applies to all students and peer quality might change. And without equilibrium model, you cannot predict what peer quality will be in the new environment. And therefore, you can't predict outcomes under the new policy. Yeah. Okay, so I'm going to use my paper with Paulo Borden in 2015 to illustrate this equilibrium study. So we developed an equilibrium college major choice under college major specific admission system, the joint system, with a few components. First, students are uncertain about how good they are at different majors. And there is endogenous peer quality that would affect individual outcomes. And we apply our model to the Chilean setting. So Chile uses the same college major specific admission system like the Chinese system. Okay, so and then in our counterfactual experiment, we're going to solve for new equilibrium in sort of in a game between a social planner and potential college students. So the social planner would choose college-specific rather than college major-specific admissions policies. And the student would make their enrollment decisions, learn about their fits, and then choose majors. Okay, so we start the estimation from the joint system, where you have to make a college major specific choice at the very beginning, and then we change it to the US system. Okay. So a little bit of background in education in Chile. So it's very similar to the Chinese system. In the 11th grade, students choose to follow one of three tracks: humanities, science, and arts. And then after that, they receive more advanced training in the subject of their chosen track. And college admissions is based on the single admissions process called the University Selection Test, PSU. And it's very similar to the National College Entrance Exam in China. So you take exams in math, language, and social science related subjects and science related subject, depending on which track you are on. And the admission is college major specific. It's based on a single index. So the index is a weighted average of your PSU test scores and your high school GPA. The weights differ across college programs. For example, engineering major would give more weights on math, and journalism would give more weights on language, so on and so forth. And the student is admitted to the college major if her index is above the cutoff. Very transparent, very just one index, uniform, unidimensional. Okay. So how do we model this baseline system? So we model a continuum of students. Those are potential college enrollees. And there are J colleges, each with M majors. A college program is a pair, JM. And college admission is subject to program-specific admission standard. By program, I mean JM, college major pair, okay? And there is an outside option to all students. So students have a vector of observables, gender, family income can be low or high, and abilities. So like I said, we're talking about major specific choices. So you need to have multidimensional abilities rather than one dimension, okay? So how do we model this? So there is multidimensional knowledge reflected in your test scores, math, language, so on and so forth. So we have observed a vector of test scores. And remember, different majors use different weights to combine these test scores into one index. And that's how we model the major specific ability. So use a weight, that's omega. That's omega m is a weight that major M gives to the specific dimension of the test score. Okay, so that gives you a major specific ability. That's how we model multidimensional ability. Okay. Yeah. Yes, of course. The difference mainly comes from cross majors, not cross universities. The weights are, you can think about those weights are some sort of technology, right? So different majors use different technology, but different schools, maybe that difference is very small. Okay. And there is some consumption value of going to a particular program. So VJM is the value, not the consumption value of going to program JM for this student. So what it is, so this big AJM is the average major M ability among students attending that program. Okay. So it's the peer effect out there, and we're just making things simple by assuming only the mean matters, okay? A linear means peer effect. We're not talking about whole distribution matters. In a more general model, you can think like the whole distribution of your peers matter. But here we're only talking about the mean, okay? So that's an assumption, also a limitation. And epsilon is just an IID individual taste. And X is your own characteristics, your gender, your ability, and your family income. Okay, so the net consumption value of program is just a function of these things. Now, how do we model? Yes. That's the one of the most important factor of this model. It's coming. Okay. So how do we model major? What is a major? Of course, we have some qualitative sense of a major, but how do you model it quantitatively? Okay. So this is how we model a major. A major is basically a course bundle. Okay. So different programs use different bundles of courses. And it's these bundles of courses that are the building block of your human capital. Okay. So a student learns how efficient you are in each type of courses after being exposed to it. You have some ex-ante ability, that's a vector. And then after you take a math course or an econ course or a music course, you learn how good you are in that course. Okay. So major specific human capital production in this program is going to be a function of your major specific ability, your peer quality, and your own efficiency at different courses. Okay. Your efficiency in a course A would matter more if course A receive a lot of weights in this major. Okay, that's how we model major. Majors are just different bundles of courses. Okay. And wages are major specific functions of your major specific human capital, your experience, and transitory wage shocks. We have wage because wage is something we can observe. Human capital is something we don't observe. Okay, so you need some measurable outcome. That's wage. Okay. Questions? Yeah. Quality is going to be embedded in peer quality. So in our model, given the data we have, it's almost impossible to distinguish between how much is college quality, how much is your peer quality. Yes, peer from your own major, yes. It's not a general equilibrium model. Ex-ante not, because they don't even know their major specific efficiency yet. But once they learn about major specific efficiency, then they know the expected wage. That's the uncertainty. The bigger uncertainty you face is you don't know your ability in different majors, your ex-post ability in different majors. Yes. Can they change their major? So in the Chilean setting, it's almost impossible. Because when I talk about empirical setting, you will see we're not modeling 1,000 majors. We're just modeling big categories of majors. Switching across big categories, that's a zero probability event. Okay, timing of this model, simple. First, students make college major specific enrollment decisions subject to the admissions cutoffs. Then a college enrollee in major M, remember, this is the setting where you have to claim your major right away. Okay, so your enrollee in major M learn how well suited she is to that major and decide whether or not to drop out. And if you choose to stay, you spend one more period in college and then enter the labor market. And we can solve the model better. Okay, continuation. Given, remember now, is a case where you already taken courses in different in different courses. You learn how good you are in those courses. You have a sense of your major specific ability. Okay, ex-post major specific ability is realized. You decide whether or not to go out. And then enrollment is assume that students are rational. Okay, given the equilibrium ability, peer ability distribution, and the program specific cutoffs, you just choose the best among the programs that you are admitted to and the outside option. Very simple. Okay. So the equilibrium, look at this. enrollment decision period, the big AJM is taken as given by an individual student, but that's equilibrium object. So equilibrium requires that each student make optimal choices, enrollment choices and dropout choices given the peer quality. But peer quality has to be consistent with student individual choices. Yeah? Questions? Yep. In university factors in terms of what? You mean in a counterfactual? In a counterfactual, we could. In the estimation, we don't have that because it's a centralized admission system, and like I said, students pretty much can't transfer to a different major. Okay, so the data sources, we have the entrance exam scores and their enrollment from the Department of Education or Evaluation and Education Testing Service. We have from the Ministry of Education in Chile, we have the wage data, post-education wage data. We have college data. We have college major specific cutoffs. We have the weights that used to form the major specific ability index. We have the tuition. We have enrollment in consecutive years. Okay, those are the data. Yes. We don't observe application list, nor do we model application. So the model is simplified in the sense that we assume that students are just choosing the available. By available, we mean as long as you're above the cutoff. Okay, you choose the best among the choices that are you are eligible for. We're abstracting from application, strategic application. Yeah. No. That's totally a equilibrium object. Yes. Okay. Yeah. They have double major. I don't know. I have to ask Paula. Where's Paula? Chile. I don't think so in our data period. Okay. So there are a lot of colleges and a lot of majors in Chile, but we can't handle that many. So that's another limitation of this paper. So we have to do some aggregation. So first of all, we aggregate into 3 tiers by prestige and student quality and admission standard. By the way, these are the colleges that are in the centralized system. Those are good public colleges. And there are also sort of an outside option in our model composed of some low quality private schools, private universities. So here we're focusing on the centralized system, okay? So we just aggregate these 25 universities into 3 tiers. And then we also aggregate hundreds of majors into 8 categories by similarity in terms of the course bundles, in terms of their admissions cutoffs, in terms of the mean wage post-education. So we have these 8 majors. So business, law, education, engineering, science, arts and social science, medicine, and health. Medicine is doctors, health are nurses. Okay, those are very different majors. And that's the distribution of students across tiers. by construction, most students are outside option. These are the elite colleges, so to speak, the 3 tiers. And some summary statistics of major. So something that's interesting here, so this column is their math scores in the exam, in the entrance exam. This is language scores. I'm highlighting a few rows here. First of all, if you look at medicine, these are just absolutely good students in both dimensions. Okay, so if you look at engineering, they're good at math, not that good at language, and the opposite is true for arts and social science. So students have ex ante comparative advantage. And in medicine, in case of medicine, it's just absolute advantage, yes. Potential college enrollees, including all high school students who took the exams, okay. So outside option include everything that's not in our 26 schools, 25 schools. Yes, 25 universities. Yes. Questions? Okay. Okay, so we estimated this model using GMM, and the moments, the key moments, there are other stuff we target, but the key moments are the enrollment across tier, and student ability by enrollment status, and the retention rates by tier and major. And the wage data, we have wage levels, wage growth, and the graduates' ability. Okay, those are the key moments we target. Okay, so let's do counterfactual. So I'm not going to show the model fits. They're good. Okay, so the counterfactual environment is the US system. Okay, instead of college major specific cutoffs, we're going to have college specific admissions. And then once you are admitted to a college, you choose a major after you learn about your fits to different majors. So how do we model this system? We want to keep the centralized flavor of admissions. In the baseline, it's a centralized system. So in the counterfactual, we want to keep it as a centralized system. So that's why we created this planner. The planner maximizes the total student welfare by making admission policies. And we want to put some constraint on this planner so that the comparison between these two systems is fair, so to speak. Okay, you can't give the planner the information that was not available under the baseline. Okay, so the constraint is, first of all, if you admit a student to a higher tier college, the student is also admitted to a lower tier. You can't name the student, you have to go to number 1. You have to go to number 3 now, okay? You can only have a cutoff, sort of which tier you are good for, up to which tier, okay? So that's the first constraint. The second one is the planner can only use student ability to distinguish students. You can't use student preference to distinguish them. Okay. Okay, so then the counterfactual, this is basically the sequential system. Stage 1, the planner announced college-specific admissions policies. Stage 2, students make their enrollment decisions, choosing one of the college that they are eligible for or the outside option. And then if you enrolled, you choose the intensity, the course taking intensity across majors. How many courses to take from econ, how many courses to take from engineering, for example. Okay. And then last stage 3, An enrollee learns her efficiency in courses you have taken. If you don't take that course, you don't know your efficiency in that course. If you take that course, you learned about your efficiency. Again, this is another simplification. In reality, you would imagine that it's not totally you learned it right away. You gradually learn it. But given the data set we have, the kind of information we have, it's really hard to do this continuous learning. So we're just do it like in a snap, okay? Once you take it, you know it. So the conditional on ability, that efficiency post as course efficiency is the residual part that's independent of ability. You know the systematic part of the ability. That's already an input in the production function. What you don't know is the sort of the random part. Yes, because the planner already told them. Yep. The planner is going to take that into consideration, not the individual student. Okay, the planner's problem is harder here, but not the student's problem. Okay. So then, okay, stage 4, a stayer spend enough time in college to finish the requirement of your major choice, of the choice of the major of your choice, and then enter the labor market. How long is enough? You have to stay enough time so that you can fulfill the requirement. For example, econ requires 20 courses from econ courses. If in the first period you take only 1 course in econ and you choose to do econ, you have to spend enough time to finish the 19. Okay, so the duration is going to be an endogenous function of your first course bundle choice in the first period. And students take that into consideration when they try to explore. Okay, here is the trade-off. You have a trade-off of breadth and depth. Okay, so exploring more allow you to learn more about your major specific ability in different majors, in a lot of majors. But the cost, the downside is then you have to spend more time to finish your final major. Okay. Yep. That's an equilibrium object. I don't make assumptions. I make after I know student preference parameters, I can simulate that. I can solve student problem. Capacity constraint in different majors. We are talking about that. Yeah, so in the baseline counterfactual, we don't have capacity constraint, and then we have another counterfactual that take that into consideration. Basically, here in stage 3, your choice is constrained. Okay, only the good ones, the ones that can pass the major specific cutoffs can, or the requirement can enroll in that course. So that's a counterfactual we can consider. We did consider that. Yeah. So we don't have effort choice in the model. What we have is your your productivity or your human capital is going to be a function of a major specific function of your peer's quality. The peer can be useful for you. For example, in our estimates, in some majors, peers are useless. In some majors, peers are super important. So, you guys have already mentioned that the problem here, the planner's problem is a little bit complicated here. So let's think about the planner's problem. What are the factors to consider when you make admissions decisions? Suppose I'm faced with a student with ability A, ability vector A. Okay. So of course, where should I admit this student? I care about the individual student's welfare. Okay, I care about this student per se, but I also care about this student effect on her peers' welfare. That's an externality that students themselves do not take into consideration, and the planner has to take that into consideration. The externality comes from two sources. First of all, the market return. Your ability would affect your peers' human capital production. That's the first layer of externality. The second layer is effort cost, or the preference or the utility in college. You would affect your peers' utility in college. Okay. So then the planner would compare different admissions decisions and choose the best one. So as you can see, optimality would immediately imply that admissions policy would depend on the whole vector of your ability, not just an index. Okay, an index is almost never going to be optimal in this case. You have to consider the whole vector. Okay, but that's a detail. So overall, the optimal admissions policy will guide students sorting toward the maximization of total welfare. Why guiding? Because you cannot force a student to be in a specific program. Yeah. Yep. So we are just basically thinking if you don't even take science for test, you are not eligible for any science related majors. Yeah, the same for social science. If you don't even take the social science test, you are not eligible for social science majors. Different, yeah, yeah. No, no. Ex ante, yes, yes, because we want to be fair between these two systems. No, the planner would form expectations, and then ex ante, what's the best choice for the student? What's the best admission set for this student? Yes. Can you speak up? Thanks. Yes, it would. If there are new majors, it's not in the model. If there are some new outside options, then that would change the outside option value. So that would make the preference, so to speak, preference parameters policy variant. And then I can't conduct the policy counterfactual. Okay, that's a good question. Basically, here is assuming the set of college majors are fixed and the outside option is fixed. Okay. Yes. In the extended counterfactual policy experiment, yes, there will be capacity, and we handle that. Not optimal capacity. We take the capacity as given, and then just choose the sort of cutoffs in the second period as well. So there will be admissions in the first period, and then also a sort of a requirement in the second period. Only those who meet the requirement can be can choose that major. And in equilibrium, once you impose that restriction, your capacity is not going to explode. And that's also an equilibrium object that you have to simulate. Any other questions? No, first of all, the Chilean system is similar to the Chinese system, but not exactly the Chinese system. In China, you have each province get a quota from a college. No, in Chile, it's totally centralized. Okay, so the quota is just the total capacity of that program, and no matter where you're from. And secondly, there is no tuition difference between local student and student in other states or something like that. That's a U.S. system. Yeah. Okay. Good. Okay. Okay. So that's my counterfactual. Let's see the result. So the baseline is the joint system, and new is the counterfactual environment I just talked about. The planner is choosing college-specific admissions. As you can see, we have higher enrollment, and we have higher retention rates, and we have higher welfare. That's per capita per student welfare. Okay. Per potential enrollees welfare. And that's what's interesting is this table, I think. Here we just divide students by their test score quartiles, the lowest quartile and the highest quartile, okay? So as you can see, in terms of enrollment, it increases across the board. In terms of retention, it increases across the board. In terms of welfare, higher for the first quartile, higher here, lower here. Okay, so how come this would happen? Okay. In the baseline, you are admitted to a specific major. In the counterfactual, you are admitted to certain colleges, and then you choose your major. You can do exactly what you did before. In the baseline, you specialize right away, right? And in the counterfactual, the worst you can do is to specialize right away. That's an available choice. And in an individual decision model, that's expanding your choice set. And in an individual decision model, that would never hurt you. That would never hurt you in a rational model, at least, unless you introduce some behavior assumptions that's a different story. But we're in a rational setting. Why would this happen? Why these students are worse off when their choice set is expanded? Peer effect. Because in a counterfactual, these students, for example, those medical students. They used to be together with the highest ability medical students. Now, the planner admits students into college, and some of the low quality students would enter medicine major. And that would lower the peer quality in those best programs. That's why the student welfare decreases. Okay, so this is an example where the counterfactual predictions out of an equilibrium model differs not only quantitatively, but qualitatively from the individual decision model. Okay. Worst. Okay, so then this is sort of a summary table of who's better off under the new system. Okay, we can just do the welfare change, welfare increase, welfare didn't, welfare gain is 0, welfare gain is negative, like 3 outcomes, and run those outcomes on student characteristics. This is just a way to summarize who's better off, who's worse off. Okay, so as you can see, females are better off, low-income students are better off, and this is basically a measure of the your comparative advantage, so to speak. The difference between your language score and your math score. If the difference is large, that means you have clear comparative advantage. If the difference is small, you are perhaps less certain about what you are good at. Okay, so here are the students. If you have a clear comparative advantage, then this system is going to hurt you. Yeah. Okay, that's not so serious in terms of what? This is order loaded. It's not in terms of pieces. This is a order loaded. Yeah. So that means it sort of says the joint system where you have to claim a major right away favor more advantaged students. And a switch into the sequential system could improve equity. Okay. So sort of a small conclusion from these two examples, the individual model and the equilibrium model, is that structural approaches allow researchers to conduct counterfactual policy experiments and therefore provide information for policymakers without having to run costly social experiments. The benefit comes with the cost of course, you have to make assumptions and impose structure. And in terms of individual decision model versus equilibrium model allows the researcher to study larger scale policies, but at the cost of making even more assumptions. Okay, there's no absolute good choice or right answer. The modeling choice depends on what question you're trying to answer. Yeah. Okay, so I have 30 minutes, right? Okay, so let's. Okay, so I think I can do a little bit of introduction of this. It's like an, oh, I just realized I didn't. Where's Zoom? Oh, here. Yes. Go ahead. Yes. Yeah, go ahead. I can't answer that question because in my model, I didn't have school. So if I model schools, for example, in the decentralized setting, I can by review preferences to estimate schools objective function, where I impose a structure on what kind the multiple factors the schools are interested in, and then I can estimate the weights on different factors. And then I can answer your question. But in that model, in the model I just showed, I don't even have a school. There's no notion of school. So I can't answer that question. Okay, so another example of modeling choice is the study of crime. I can use, yes. Okay, so when we talk about policies to prevent crimes, it's really hard and costly to implement. You can either directly through law enforcement or indirectly through programs such as education and housing and the social welfare programs that can also indirectly reduce crime. And designing such policies require knowledge about their impacts, of course. And one way to obtain such information is through social experiments. But in terms of crime, especially, this can be very costly or even cross ethical boundaries. You can't do a random allocation of, two identical criminals, one sent to 10 years in prison, one sent 1 year in prison. You can't do that. And a different way is to use a structural approach. And structural approach build and estimate models of crime that explicitly study how individuals make decisions and how crimes rates are determined. The benefit of this is capable of predicting impact of various counterfactual policies, but the cost is assumptions you have to make. Okay. And there are two types of structural models in this literature. By two types, I mean a very narrow sense of two types. One that focus on individual decisions. Another one that embed individual decisions into an equilibrium framework to study the determination. So similar to my previous discussion about college majors, I'm going to use a few examples to illustrate individual decision model versus equilibrium model in the context of. Okay. So the main goal of individual decision model is to predict how individual choices might change if policies changes. The typical framework in terms of crime is discrete choice dynamic programming models. And the assumptions typically made in this literature is the following. First of all, individuals are rational and forward-looking, and the individual make decisions by comparing current and the future benefit of different choices. Once you make that assumption, that means when you change policies, you will change the relative benefits of criminal versus non-criminal activities, and that will change crime participation. Okay, that's the first assumption. The second typical assumption is that individuals have objective and correct perceptions about arrest rate and job market prospects. This is a very, very strong assumption. Okay. And arrest rate is observed at the aggregate level, because at the aggregate level, you know crime rates, you know how many criminals are arrested, so you know the arrest rate. And there is no individual level data about arrest or crime, okay? Because the crimes that we observe are arrested crimes. So you can't allow for individuals to have heterogeneous beliefs about the arrest rate. Then the model is fundamentally not identified unless you run a survey about to elicit those beliefs. Okay, so this is a strong assumption, and due to the particular situation we're talking about. In a typical data set, you never observe individual level crime unless the crime is arrested. Okay. Okay, so examples of this kind of individual decision model, one is Imai Krishna 2004 in IER. Another one is my paper with my co-authors in Chile. That's 2022. Both these papers about teenage crimes. So teenagers are sort of the prime age of crime. Okay. So in our paper, we consider 4 factors. It's an individual decision model, and we consider 4 factors underlying choices made by teenagers. First, teenagers, by the time you are already a teenager, you have heterogeneous endowments. You have different family background, you are enrolled in a different primary school, and you have some observable preferences and abilities. And second factor is institutional frictions. So you are facing unequal opportunities. For example, you have different unequal access to high quality high schools. Okay. And the third is information friction. So similar to the major choice, but here is you have uncertainties about your academic ability and therefore your future prospects. The fourth is just luck. Some contemporaneous shocks and noises, and these can have long-term impacts through the dynamic choices. Okay. So in our model, a teenager makes decisions on basically 4 choices. School and crime. You can do nothing, one of them, or both of them. Okay, so 4 choices each period. And if you choose to go to school, then you observe your GPA. Then you update your belief about your academic ability by using the GPA. GPA is a noisy measure of your ability. Okay, so you do Bayesian updating. And if you do crime, you can get arrested. With some probability, you're arrested. And if you are arrested with some probability, you will face a distributional penalty. Okay, and this distribution would vary with your criminal record and age. So this variation here we introduced is following basically the policy that's really implemented in the data. Okay. And teenagers' decision is made because you don't know your ability. So it's made on your expectation about your subjective beliefs about the benefits of each choices. The expectation is based on your updated belief about yourself. Okay, so it's a very simple dynamic programming problem. And we estimate this model using 3 data sets from Chile that are linked at individual level. So the panel of student records and standardized test scores and family background survey and the criminal record of all arrested teenagers, and these data sets are linked. The data here is sort of nice because in a lot of other countries, teenage crime are sealed. You can't observe those, yes. Good question. No, for exactly the same reason I mentioned. Crime is observed at the individual level only when the individual is arrested. So that means fundamentally, I can't allow for individual specific ability of committing crime. Because that would imply, for example, individual specific arrest rate. And there's no identification because I don't observe individual specific arrest rate in the data. That's another assumption. So in any crime paper, unless you use individual level survey to ask about, did you do a crime? Were you arrested? This kind of questions. And if you believe those questions, then you can have individual specific arrest rate. And other than using that kind of data, every crime paper has to make this strong assumption that everybody face the same arrest rate. That's just a data limitation. You only observe arrest rate at the aggregate level. Okay, so I know who are your classmates. We started thinking about peer effect in this model, but in terms of crime, your peers are not your classmates. Your peers are the student, the kids on the street that I don't know. Okay. Okay, counterfactual policies, then, it's a very simple dynamic programming problem, and we're interested in individuals' choices when you do targeted intervention. Okay, so we got counterfactual policies. We change the environment for a disadvantaged teenager without changing his initial conditions. So we reduce institutional frictions, basically give the disadvantaged teenager the same access to good high schools. And that would reduce the ever arrested teenagers by 44%. And we could also improve your current school situation. We can enroll a disadvantaged teenager to a sort of an average primary school. We don't want to do unrealistic intervention where we put you to the top one, number one private school. We just put you in a sort of an average school, okay? And then that would reduce teenage crime more than the first counterfactual. And then the third counterfactual, we basically enhance both 1 and 2 with full high school tuition subsidy. That would double the impact of both policies. Okay. So our goal is very humble here. We're just asking, if I give this individual student certain special treatment, what would happen to this student? That's it. So it's an individual decision. Okay. Okay, 15 minutes. I'm going to run. Equilibrium models. Okay. So modern literature, starting from Becker to 1968, recognize that crime rates are equilibrium outcomes. So you have a supply of crime. Basically, citizens choose supply of their labor to legal versus illegal income generating activities. That's the crime supply part. And you also have a demand for crime. What do we mean by demand? That's policymakers choose the level of resources committed to preventing crimes. How many police officers you have, how strict the legal system is, something like that, right? Okay, so the typical framework in this literature equilibrium is static equilibrium models. Okay, it's static, it's not dynamic. Okay, that's still dynamic equilibrium model in this setting is really hard. Okay, so typically it's static. And typical data set used, if we're talking about US setting, then that's the Uniform Crime Reports and the Current Population Survey. And examples of this equilibrium framework, one is IER paper, 2000 IER paper. Another one is my paper with Ken, 2018. Okay, so I'm going to use our paper as an example. So this paper is motivated by the sort of a policy question. Reducing crime is a long-term policy goal in the US government. For example, this COPS program initiated by Clinton administration planned to add 20% more police nationwide by 2000. And this policy is still going, although it was old, but it's still going on. Okay, and since 1994, this program has provided a lot of money to assist state and local law enforcement agencies to help. Basically, the policy is to help. Why it's called COPS? It's a very nice name because it help you to hire more cops. Okay. So the question is, what will be an optimal way to allocate so much money? Okay. And the answer depends on how local government and their citizens would react to this federal program. And in order to achieve that goal, we need to understand how crime is determined in the equilibrium. Okay. So to answer that question, individual decision model is no longer sufficient. We need an equilibrium. So our model is a static Becker type of model. We have a local government, let's call it a city, and its citizen. Individuals in this model choose among three options: work, home, crime. And individuals have different human capital. They have different values of staying home, and they have different psychic cost of committing crimes. And these heterogeneity are treated as unobserved heterogeneity types. And these types are correlated with observable pseudodemographics that we can observe in CPS. And the distribution of types could differ across cities. So there is heterogeneity at the city level and at the individual level. And the local government, each government chooses how many policemen to put on the street. Their objective is to minimize a cost. And the cost, if you have high crime rate, it's painful. If you hire a lot of policemen, that's painful, that's costly. And if you can't arrest anybody, that's also painful. Okay, so that's the objective function. We're going to just estimate the weights on different components. The components are imposed. That's our assumption, but the weights are to be estimated. Okay. So we're just assuming that local government is a decision maker. It's an optimal decision maker and abstract from political concerns. And cities differ in terms of their productivity, the legal sector productivity, their police efficiency, how easy it is to catch a criminal, and the marginal cost of policemen. So that's basically the opportunity cost of spending $1 in police versus any other use. Okay. So this model incorporates these following outcomes of an equilibrium. The number of policemen on the street, that's chosen by the local government. And the crime rate, that's chosen by citizens. The arrest rate, that is a function of how many policemen you have and how many criminals you have. Okay, I'm going to come back to this later, but this is a whole headache. Okay. And the employment rate is also endogenously determined because that's just a fraction of citizens that choose to work. And the rental rate of human capital, that's just a decreasing function of the supply of labor. Okay, the marginal return to labor. Okay, so the highlighted part, the arrest rate, is a function of both the number of policemen and the number of criminals that cause multiple equilibria. Because there is a spillover effect of crime on apprehension. Let me be more specific. So let's say given a police size, okay? Fix that. And then if you have a fixed number of policemen on the street, when crime rate goes up, what happens to arrest rate? Arrest rate goes down because you spread, the policemen have to spread things, okay? So you have, and if arrest rate is low, what happens? You induce more people to commit crime because the probability of getting arrested is low. Therefore, you have a self-fulfilling high crime equilibrium, okay? On the other hand, given exactly the same number of police on the street, if there are few criminals on the street, what happens to arrest rate? Arrest rate is high. 2 policemen is taking care of 1 criminal, they're going to catch you, okay? But if arrest rate is high, what happens to crime rate? Very few people dare to be a criminal. Therefore, you have a self-fulfilling low crime equilibrium. That's a headache when you have arrest rate as a function of both number of police and number of criminals. However, that's a very realistic description of arrest. And we don't want headache per se. We hate headaches, but it's a headache we have to take. Okay. So this multiplicity is inherent property of the structure. However, generally speaking, characterize the set of all possible equilibria is infeasible. So what we ended up doing is to assume certain functional forms. Those are strong assumptions. But under those strong assumptions, all potential equilibria can be computed and they are ranked by crime rates. The number of possible equilibria is bounded by the number of individual types. So it increases linearly with the individual types instead of exponentially. So that makes the problem feasible. But the cost is it requires specific functional forms. Okay, as you can see, this is a non-trivial trade-off. It's very strong assumption on the functional forms, but without that, the problem goes out of hand. Okay. So the government problem is basically realizing when you choose police force, it will affect the set of equilibria because given a number of policemen, you have multiple equilibria. So what the government can influence is which equilibria are possible. Okay, you can't choose one equilibrium as a government. You can choose the set of equilibrium that's possible. Okay, then the government make decisions to minimize the expected loss, where the expectation is taken over the possible multiple equilibrium. Okay. So then we use data from CPS and the uniform crime rates, and we use GMM to estimate parameters that govern individual preferences, government preferences, technology in terms of arrest technology, in terms of legal sector, production technology, and the distribution of observables across individuals, conditional observables, and the distribution of observables across MSAs. So a CD in our empirical setting is an MSA, not a CD. Okay, and the distribution of multiple equilibrium, basically equilibrium selection rule. Again, based on some assumptions that make the identification feasible. Okay, so this, we built a sort of a big model, but we don't like big model per se. We like big models because it allows us to do stuff. Okay, so using that model, we did a whole bunch of counterfactual policy experiment, but we can characterize it into three big categories. The first set of counterfactual, we increase the police force uniformly across MSAs. And then we calculate the cost at the federal government level and the crime reduction nationwide. Okay. And then that's sort of forcing every MSA to increase police force by a certain percent. A more realistic counterfactual is to say, okay, as a federal government, I'm going to subsidize a certain fraction of your new policemen. Whether or not you take it is your individual local government's choice. If you take it, I'm going to take certain fraction of your total cost, and you're responsible for the rest of the cost. Or you can just leave the money on the table. Okay, so that's the second set of counterfactual. The third set of counterfactual is sort of targeted resource allocation. So given a fixed budget at the federal level and a given policy goal, for example, you can say, I, as a federal government, I want to reduce the total crime rate, minimize the total crime rate in the nation, and I have a fixed budget. Where should I spend the money? Do I spend it in Philadelphia? Do I spend it in Phoenix? Those two high crime rate cities. Or what's a fraction to spend in each city? Okay, that's sort of targeted counterfactual we run. And we show the sort of the benefit to cost ratio across these different counterfactuals. Yes. Oh, sorry. So our crime means economically incentivized crimes, or economic sort of stealing, robbing, and all those things. Not murder, not like suicide or something. Yeah. No. Yeah. Yes, because if you are a citizen, you lose a fraction of your income to criminals. Your income is at your individual level, and the more criminals you face, the higher probability you would lose a fraction of your income. That's how we model the sort of the, in your words, spillover. Yeah.